in general, our group works on two different things. On one side, we do a lot of field work and field measurements, looking at methane emissions from the oil and gas industry, looking at the effectiveness of new technologies and how it can be incorporated in methane mitigation policies around the world. On the other hand, we also work a lot on modeling sort of to understand the future of natural gas in the carbon constrained or in the decarbonized world. Just last week, I gave a seminar at the Payne Institute in Colorado, looking at the future of LNG. We also have teams that develop models to understand the effectiveness of long-term policies to reduce methane emissions from the oil and gas sector. So what I thought I'll do today for this seminar is focus on the fieldwork side of our work. Fieldwork, as many of you know, is incredibly challenging to do. And so it's not just me, there's a whole host of people behind the results that I'm going to be presenting today. And the picture you see on the title slide is just one group in one study. This was the Alberta Methane Field Challenge that happened outside of Calgary last year. We had about 12 different teams come in, and we had about 4 or 5 universities working together to do this field challenge. So what I'm going to be doing today is sort of not present results from one study, but combine the results of a few studies together to talk about what we know about methane emissions and what does that mean for new technologies to improve upon what we already have in terms of methane mitigation programs. So the first part of my talk is going to focus on the rationale for new technologies. Why are we interested in new technologies? And many of you might know the reasons that I'm going to be talking about, but for some of you, it might be new, and I thought this might provide a good introduction. All right, so the current approaches to methane leak detection are often not well suited for our evolving understanding of methane emissions. So the video that you're going to see right now is that of an emission from a tank. That was taken, I think, in North Dakota a couple of years ago. And it was taken using an optical gas imaging FLIR camera. And you can see the methane clearly billowing out of that vent above the tank. So how does current policies work? Most jurisdictions right now say that you have to use optical gas imaging based cameras and do leak detection and repair surveys, which is basically walking around every single site, looking through the camera at every component and checking whether they leak methane. In this case, this tank was emitting methane. And so you have to do it once or twice or 4 times a year, depending on what type of site and which location you are in. Then the rule basically says if you find a leak through the survey, you have to fix it within 15 days. Typically, when you do these walking surveys with the camera in your hand, you can cover up to 3 to 5 sites a day, depending on how big the sites are and how far apart the sites are. And the cost is roughly $600 a site. That comes to around $3,000 a day, depending on which vendor you talk about. Now, it's not that this type of surveys to manage methane emissions do not work. In fact, we recently wrote a paper that showed that these repeated leak detection and repair surveys do work in reducing methane emissions. The problem is the OGA-based surveys are sort of time-consuming. If you have hundreds and thousands of sites and you have to go to every site constantly and with higher and higher frequencies over time, then that becomes expensive and time-consuming. And until you come back to a site, you don't really repair anything between 2 different surveys. So figuring out how to improve the cost effectiveness of methane mitigation is one of the main reasons why we want to look at new technologies. So what do we have in terms of new technology? So this sort of cartoon or comic tells you where different technologies are placed. So on the x-axis, you have spatial scale in meters. So on the leftmost side, you have components, 1 centimeter size components. On the right-hand side of the x-axis, you have very large-scale emissions, so measuring emissions across basins and continents and countries. On the y-axis, you have the temporal scale. You have emissions that can be measured in seconds and minutes, and then you have emissions that are measured over the course of a decade, sort of continuously or quasi-continuously. And within this matrix of space and time, you can place many different technologies. So for example, You have something called as mobile ground labs, which is basically a fancy name for putting a sensor on the truck and driving around to check for emissions. It works around the scale of a kilometer to a mile, so you can drive on roads and look for emissions. And emissions can be found in the span of a few minutes. These are often used for what we call screening programs. So what you do is you drive quickly on roads, find out sites that are emitting a lot of methane, and then tell someone to go and check that site and figure out what's wrong. So this is a screening method. You screen the sites, find out which ones are high emitting, and send a follow-up crew to actually fix the emission. And then you have something like drones. The drones right now, they typically have a 45-minute flying time, depending on the battery life, but those are improving. But drones are helpful in scenarios where access is restricted. For example, you have a safety hazard, a person cannot directly go near that equipment or that facility, then you can send a drone to measure emissions. The other advantages of drones could be that, if your emissions are at varying heights, so a flare stack can be anywhere between 20 to 30 meters above the ground, a drone can fly nearby and measure and see if there are methane emissions leaking from its stack. And the last thing I want to show you is sort of satellites. These are something that once you launch are there in space orbiting the Earth for like 5 to 10 years, and it measures methane emissions on a quasi-continuous basis. Typical satellite revisit time can be 1 to 2 weeks, but if you have a constellation of satellites, you can do daily, even sub-daily monitoring. Until recently, most satellites had spatial resolutions of about 7 to 10 kilometers. So you can talk about regional emissions, but not emissions from a single facility. But satellite technologies are improving. We have new companies and new technologies being developed that improve on the spatial resolution, and perhaps one day we can use satellites for facility level emissions measurement. And in the top left corner, we have continuous monitoring systems. These are basically like your fire alarms at home. You just put one on the site and it sends an alarm or flags the operator whenever it detects an anomalous methane emissions. And so what this tells you is that there's a whole variety of new technologies that are being developed, and not all of them will be applicable at all the sites. So we have to think about, where are these technologies going to be most effective compared to what we are currently doing, which is with the FLIR cameras. All right, so before we talk about adopting these new technologies, we have to demonstrate something called as equivalence. Now, what does equivalence mean? It basically means it's asking the question whether new technologies can reduce methane emissions as effectively as OGI-based approaches. OGI-based approaches, if you remember, is what currently being used in many regulatory regimes in Colorado, in California. And we sort of developed a framework on how we can demonstrate this equivalence. So it contains basically 3 different elements. The first one is control testing of new methods. This is where we take technologies to control sites where we know exactly where and how much the methane emissions are, and we ask the technologies whether they can see it and measure it. The METEC test site in Colorado is a great example of such a facility where you can do these tests. There have been many studies that have already done these kinds of things. There's the Mobile Monitoring Challenge. There's a monitor program that DOE sponsored a couple of years ago. Just recently, Evan and Yulia also tested a new technology through control release tests. Then there is modeling long-term mitigation. These control tests, they tell you only what happens at one time. But if you want to understand methane mitigation, you want to know what happens to methane emissions over time when you have these technologies undergo leak detection and repair surveys. And for that, we need a lot of modeling because we don't have the luxury of conducting a live experiment over 5 years to see what the effectiveness is. And so that's something that we are working on called the Path to Equivalence Framework. This is a collaboration between us, Colorado State University, and UT Austin to sort of meld 2 different models. We have a MEEP model, which is basically telling you what are the emissions at an oil and gas site. And we have the FEAST model that was actually first developed at Stanford that basically tells you what would be the effectiveness of new technologies in addressing long-term methane emissions. And those 2 things, the control testing and the modeling, are happening simultaneously right now through different projects. What I'm going to talk about today in this study are field trials at oil and gas facilities. So we're going to talk about what field trials tell us that we cannot find or know from these controlled release testing studies. So before I get into the details of what these field trials show us, I want to take a few minutes and 3 or 4 slides to talk about, what are the properties of oil and gas methane emissions where these new technologies are helpful. So in part 2, we're going to look at the features of methane emissions that affect technologies choice. So the next, I think, 4 slides that I'm going to show you are from fieldwork conducted over the past 2 years. It's not been published yet, but it's going to be out. It's in review, so it'll be out soon, hopefully. But it's going to show you some characteristics of methane emissions that will affect your technology choice. All right, the first one. I think many of you in this audience know this. Emissions are dominated by a small number of high-emitting leaks or super emitters. What you're seeing in this slide is a graph of the rank ordered fraction of emitters. So if you find 1,000 leaks, you arrange them from the highest emitting leak to the lowest emitting leak and calculate the fraction of their contributions. And you plot them like this. So on the y-axis, you have fraction of total emissions. On the x-axis, you have the rank ordered number of emitters. So 0 to 100% of emitters correspond to all the leaks you find. And on the y-axis, it's 100% of emissions. And what you're seeing here, this is 5 different surveys conducted across a set of facilities at different times of the year. What you're seeing across these 5 surveys is that the top 5% of emitters correspond to between 35% and 66% of total emissions. And so what it basically tells you is that if you are going to use technologies to detect leaks, you have to find these top 5% of these emitters quickly because they contribute to majority of total emissions. If you find these top 5%, you're solving 35 to 66% of your problem. And so technologies need to quickly find these large emitters, which has implication for how fast your technologies are going to be and what the detection limits are. And this sort of tells you directly that, having very, very small detection limits, being able to detect very small amounts of methane is not necessarily an advantage because most of your emissions are tied up in very large emitters. So you can have some trade-off around sensitivity to increase your speed of detection.
Hey, Arvind, can I ask some questions in the middle here?
Sure, go ahead.
So this observation of the 550 rule like this, do you normally see the same kind of heavy tail distribution for fields that are undergoing regular LDAR versus fields that have kind of never undergone LDAR before?
Oh, that is a great question. I think it's true, but I can't see your face. So sorry, apologize if I'm wrong.
It is me. I was hiding.
So some of the sites, so the studies that we have done so far, they did not have regular LDAR. There was no policy of regular LDAR at these sites. So that's a good question. But we did measure in British Columbia at a company site where the company had voluntary LDAR regularly. It was not mandated. And we still see this 550 distribution. But the caveat is that the absolute emissions are much lower at sites where you have regular LDAR, even though the distribution still looks like this.
Nice, thanks.
All right, so that's the first thing you need to remember with new technologies. What's the second thing? Emissions are dominated by vents. So again, the same 5 different surveys. The yellow bars are leaks, the green bars are vents. And on the y-axis, you have average emission rate of these 2 different types of leaks. So vents, if you don't know, are intentional process-related emissions. Leaks, on the other hand, are things that break down and emit methane that should not happen that way. So what we saw in these 5 surveys was that most of the emissions are vents, and it varied between 20 and 40% of all emissions, depending on what type of production you have, whether it's a gas site, whether it's an oil site, etc. So one of the things that came out of this is that site level or continuous monitoring technologies that we're looking at sort of need to know what the typical emissions at a site is. If it's a site that has a lot of vents, the continuous emission system or a plane-based system should not simply tag that site all the time because it's not something that's fixable, it's already there. So thinking about this, new technologies, you have to think about how to distinguish between leaks and vents. And most technologies currently don't do that. And so thinking about what kind of thresholds do we need to set so we don't end up flagging sites that are routinely venting a lot of methane, even though there's not a lot of leaks. And this is in one study. If you look at other studies, there are often cases where the leaks are much smaller than the vents that happen at these sites. All right, what's the other thing? So site production affects technology sites. In one study, we found oil sites emit about 2 to 3 times more than gas sites. So on the left side, you're looking at site level emissions in kilograms per day, average site level emissions for gas sites and oil sites. Again, split between leaks and vents, which is a yellow and gray. But you can clearly see that oil sites have a lot more emissions than gas sites. And a lot of that difference is because of venting at oil sites. What we found is that there's a strong correlation between oil sites having a number of tanks, and therefore tanks have a lot of vented methane emissions. And so depending on which type of site you're going to use your new technology at, you want to think about what kind of detection thresholds do you need to detect emissions. If you're looking, for example, in the Permian basin, which is an associated gas and oil production basin, your emissions tend to be high in terms of its volume. And so you don't need a very sensitive technology to detect those emissions. But if you go to a site like the Fayetteville or the Marcellus in Pennsylvania, which is all mostly dry gas, your average emission volume is going to be lower, and therefore you'll need a more sensitive technology to be able to detect it. All right, and the last thing I want to show before getting in the technology side is that some equipment are more prone to having high emissions and can also be intermittent. So what you're seeing here is the different components that you typically find at an oil and gas site and the contribution to emissions. Let's just take one example. Let's look at the last 2 bars, August 2019, where the blue bars are pneumatic devices. So the first bar tells you the fraction of emitters. So how many pneumatics did you find over all the components that you found emitting? The second bar in the pair tells you how much does it contribute to total emissions. So for example, pneumatics, which is a blue one, is about 40% of all the emitters we found, but it only contributes to about 15% of total emissions. On the other hand, if you look at open-ended lines, the purple one and the orange one, which is thief hatch, they comprise about 20% of all emitters found, but they are responsible for actually 60% of total emissions. So most of your emissions, 60%, came from tanks, even though they only contributed to they were only 20% of the total emitters you found. The point of this is technologies must be able to detect emissions from height because most of these tanks are quite high. And this is something we have observed at METEC for truck-based systems or continuous monitoring systems. If there's a large emission from the top of a tank, the plume could often waft right into the atmosphere without intersecting the ground-based continuous sensor or the truck sensor, and therefore the tank emission would be missed. I think this is a challenge that was observed, and this is something we need to think about when looking at new technologies at sites. And this will especially matter if the sites are going to have these technologies has a lot of tanks that emit methane. All right, so what we've seen so far are sort of the things that we need to keep in mind when making technology choices and what kind of technologies are best suited for a given type of facility. And now what I'm going to show you is some field results based on taking some of these technologies out into our producing facilities and looking at how they perform. All right, so field trials. So this is the Alberta Methane Field Challenge, and these are some of the pictures that was taken during the field. This happened in 2 different campaigns. The first one was in June 2019, and the second one was in November 2019, just to be able to accommodate different technologies and to make sure they are all safely operating in this region. All right, so we tested about 10 technologies, trucks, drones, planes, and fixed sensors at 50 oil and gas sites. One of these phases, the phase 2 in November 2019, included a controlled release test because we just wanted to look at how technologies quantify emissions over a range of methane emission rates. The baseline data collection was based on OGI-based LDAR survey with 2 different crews. We used OGI as a baseline because that's sort of the standard technology that most regulators use. And it's also the current standard for methane policies around North America. Quantification is much more challenging in the field setting. There were many different options available, including the high flow sampler. But the problem with the high flow sampler was that it will not measure all emissions. For example, it can only measure emissions that are accessible and you can actually reach that emission. So we decided to go with a different technology. This was basically, it looks like an iPad that you attach to the camera. It takes a video and analyzes the video. Using image processing algorithms, it takes out the methane pixels from the video and tries to quantify what the emissions are. It's called the Quantitative Optical Gas Imaging System, or QOGI system. The reason we used it is because we wanted to quantify every emission that the baseline survey finds, so we can compare other technologies to the baseline survey. Field coordination with site managers. So we had site managers on call. And if there are any issues we find at site, we immediately work with them to reduce those things. And the last thing is scheduling. So the way it worked is, it's kind of a complicated dance, really. Every day, the baseline crew will visit up to 3 to 6 sites because that's typically the speed of an OGI crew. And so every technology that's participating in this challenge had to visit those same 3 to 6 sites on that day. And we call them the overlap sites because the baseline team and the new technology measured that site on the same day. And if a technology is faster, they can go visit the other sites after they finish these 3 to 6 mandatory sites. We wanted to make sure there was some overlap between measurements on the same day in order to reduce the effect of temporal variations in emissions. But you'll see with the results that it is still an issue at producing oil and gas sites. And one of the hilarious things about doing field work is that we had the Slack channel going between all the teams that are out in the field. And there was a very localized thunderstorm that happened. And so we got a message from one team that's saying, storm is getting quite bad, very low visibility, I had to pull over. And then there's a second team that immediately said, weather is great here and there's no rain and we're doing it. And so these are things you cannot anticipate while doing fieldwork. So it was very challenging and very interesting to see how different technology teams sort of manage these weather-related issues as they come during this field trial. All right, so before I show the results, a few caveats about technology performance. There are several reasons why a technology might perform poorly in field tests. One is that they're all early stage technologies in development. The survey protocol can affect detection and quantification, and then you can have technology-related challenges. For example, if you're driving a truck, there are some sites where you will not have downwind access. So even if you think a component is emitting, you might not be able to measure it because you cannot go downwind of that site. There's inherent uncertainty in detecting emissions. This data collection for all teams are not simultaneous. Even though they overlap on the same day, it's not the exact same hour. And so there might be temporal variations in emissions. Of course, varying atmospheric and weather conditions affect technologies differently. And there is also errors in baseline OGI data collection. OGI is not perfect. I think recent studies at METEC show that depending on the experience of the operator, OGI-based data might also have some missed emissions in their survey data. And the last thing is temporal variations in methane emissions. Tank emissions are especially prone to be intermittent. And so if it's not emitting the moment you're there, then you will have missed it when comparing it to some other technology that might have seen the intermittent emission when it was on the site. And the last thing is site level and component level detection. Some technologies do component level emissions, some technologies do site level emissions detection. And so comparing them might be challenging just because of the way these technologies operate. And so what we're doing in this study is a comparison between an OGI-based baseline survey and new technologies. This is not an independent test of technology performance. For that, you want to take your technologies to a controlled site like METEC to be able to see how these technologies perform. So the first thing we did was quantify the performance of the quantitative optical gas imaging. We have to know if our baseline emission rates are reasonable estimates. So we had a control release test site to get an indication of error in baseline OGA measurements. So this is the test site that you see in the picture. These two yellow things that are sticking out are basically two different release stations, two release sites. One was at 5 feet, other was at 15 feet to simulate releases at different heights of an equipment. On the right side, you see a parity chart of the true emission rate on the x-axis and the QOGI estimated emission rate on the y-axis. This was a wide range of emissions from about 30 standard cubic feet per hour to about 2,000 standard cubic feet per hour, because that's sort of the range of emissions technologies typically see at oil and gas sites. What we found is that in aggregate, the baseline measurements had an error of approximately 18%. You can see in this parity chart that there are some emissions that are sort of outliers and far away from this black line, which is the one-to-one line. What this tells us is that when you're using this instrument, this QOGA instrument, you don't want to compare individual emission rates between what the instrument says and what some other technology says. What you want to do is aggregate them over multiple measurements so that you can compare aggregate measurement error from QOGA with other technologies. All right, so this is where I'm going to start talking about some of the technologies. So what we found is that most technologies are effective at detecting methane emissions, but they show significant variation in survey speed and survey times. So I'm going to show this table here, but I'm going to walk you through some of the important things that you want to talk about. So these are the different technology teams that participated. Two teams, Altus Geomatics and the University of Calgary, appeared twice because they participated both in the June campaign and in the November campaign. Roughly 2 weeks, but there were some teams that could only participate for 1 week. The TechValco and the FLIR systems, these are handheld systems. The reason they had to participate for only 1 week was because we couldn't have two handheld systems on the same site at the same time, because one could easily see what the other team is doing and go and check there, and it sort of breaks the blind of emissions. And so they had to be separated in time to be able to measure. So, all right, over the course of, so what you want to see is survey speed. How many sites per day did each team survey? So it varies from about 3 for TechValco. TechValco is a handheld system, so you basically walk around with the system and measure emissions. And it up to 15 sites per day for Altus Geomatics. Altus Geomatics is a truck-based technology. They don't go into any site. They just go on the roads or on the fence line of a site to measure total site level emissions. And so they quickly go to a site, circle the site, measure emissions, and go to the next site. And so there's a wide variation in survey speed here. What's important to note here is that Bridger Photonics is a plane-based system that has about 13 sites per day. They only flew for about 3 hours that day, and so it looks lower than what normally a plane-based system looks like. What I want to show here is the effectiveness. So what this effectiveness shows, detection effectiveness, is site-level detection effectiveness. So if a technology found emission at a site, and if the OGI baseline team also found emission at a site, then we say that they both found an emission at the site. And you can calculate across all the sites that were visited, what is the detection effectiveness. So Bridger, everyone's really reasonably good, over 80%, but Bridger shows 43%. And the reason is because it's a plane-based system, it might not detect sites that have very low emissions. So what Bridger does is they give you two different things. They give you level 1 emissions and level 3 emissions. Level 1 emissions are very large emissions. They can isolate and quantify, and they tell you exactly what the emissions are. Level 3 emissions are small emissions that they cannot quantify because it's really small. So and this 43% is only if you include level 1 emissions. If you include level 3 emissions, the effectiveness of Bridger Photonics increases to over 90%.
Hey, Arvind, this is
yes.
Erin. Question. So this detection effectiveness is just total number of leaks then?
No, it's just total site level emissions. Did this technology detect an emission at the site?
Okay, but not the mass emissions.
No, not the mass emission. This is just detection. You're correct.
So if there were a small emission detected by the OGI team, it would, and Bridger did not see it, then that would be a 0 for that site, even though the one find by the OGI team might have been small in that circumstance.
Right, that's correct. So this is just comparing to what OGI did. It's not comparing the absolute emissions levels. And so the one thing we want to, the other thing in this slide is that FLIR systems, the company came out with a new technology, an uncooled infrared detector. It's the same as a current FLIR system. It's just uncooled and I think $30,000 cheaper. They had low detection effectiveness as well. But this is something we understand very well because uncooled sensors have much lower sensitivity compared to cooled infrared systems, and therefore they detected far fewer emissions than the baseline team, which used a cooled infrared sensor. All right, so this is at the site level. Now we want to see what happened at the emissions at these levels. So this is just saying, did this technology detect emission at a site or not? But how much, how big are these emissions? And that's something we wanted to check. All right, so what this graph shows you is the same thing as before, but instead of looking at just detection, it's looking at what is the emission rate detected at sites that these technologies detected. So let's take an example here. Let's take an example of CCOPS here. That's the last but one bar. So what this does is, in this graph, what you're seeing is what is the emission rate at sites where these new technologies met. So the empty bars are sites where CCOPS found emissions and the baseline team also found emissions. And so of all the sites, the average emissions about 400 standard cubic feet per hour, and there were 35 sites. And the gray bars are bars where CCOPS did not find emissions, but the OGA found emissions. So you can think of it as where CCOPS did not see anything, and so it's below their detection limit. This is technically not a detection limit because this was not a control test. This was at a producing site. But you can think of it like this because it's analogous to that. And so at sites where CCOPS did not find the emissions that OGA detected, the average emission rate was about 15 standard cubic feet per hour. So what this tells you is that, what are the sites, what kind of emissions do these technologies see? And in most of the teams, you can see a clear discrimination between the average emissions at sites where they correctly found emissions, like the baseline team, versus the gray bars where they did not find emissions compared to the baseline team. And so what's interesting to me here is that the threshold of non-detection, so the gray bars, the average emission rate gray bars here, are often significantly higher than the detection threshold that you estimate at controlled release test site. And now, this is not because the technologies are bad or they perform worse at field sites. I think this sort of highlights the challenges of blindly translating results from a controlled test site onto a field test site. What you're going to observe at field sites are performance that are significantly worse, not significantly worse, but that are worse than what you observe at controlled test sites, because a lot of things are uncontrolled. You might have intermittency, you might have atmospheric and weather conditions that are changing. You might have to change your survey method because of some safety issues. So the detection thresholds that you might observe in the field will not be the same as what you observe at controlled release sites. All right.
Arvind, for what you had for Bridger in that plot, was that the measurements where they could quantify the leak, which I thought you said was like 40%, or where it was just binary but not quantified, which I thought you said.
Yeah. So wherever they quantified the leak, so this is what the baseline found. So wherever Bridger was able to quantify the leak, the average emission at those sites were about 450 standard cubic feet per hour. Wherever Bridger did not quantify the leak and did not find an emission, the average emission rate was about 180 or 190 standard cubic feet per hour.
Hey, Arvind, following question, this is Erin again. How are you coming up with those rates? Are you relying upon, so I guess they're all controlled release? So
this graph is the emission rate at the sites that was measured by the baseline team.
That was
Remind me what they were using?
They are using an OJ handheld camera for detection, and the QOJ, the provenance tablet, for quantification.
Okay.
All right, so some teams, so we have seen the site level data. What we're now seeing are sort of the component level data. So some technologies, not all of them, but some of them detect equipment level emissions. So here we have 5 major equipments you find on sites. You have tanks, you have wellheads, you have compressors, you have separators, and you have buildings. And these are not all technologies. These are only those technologies that measured emissions at the equipment level. What you're seeing is that in most cases, the overall effectiveness is relatively high. Again, Bridger is low because they're a plain team. They only detected at some of the sites. So I want to highlight a couple of things here. The first thing is some of the biggest variations you see are in the tanks category. So you have 0, you have 40, and you have 100%. What we found was that the drone teams are better able to quantify or detect emissions at tanks. Because when you look at how these teams operate, the drone teams actually fly near the top of the tank. And so they're often in the middle of the plume if there's a tank emission. And so they're much more effectively able to measure tank emissions. Sometimes, for example, if you look at the trucks in this scenario, it's 46%. We don't know why it's lower, but one hypothesis is that sometimes tank emissions loft directly to the atmosphere without intersecting the sensor that is on the truck. And the second obvious reason is that tank emissions are highly intermittent. And therefore, just when the team was there, there was no tank emission, and therefore they didn't see this. And we have some evidence for that, because when the baseline OGI crew went to these sites, they noted down whether the emission that they are seeing is intermittent or not. And so if we account for those intermittent tanks and redid this analysis of how effectively they are detecting emissions at tanks, what you're going to see is that almost every technology improved their tank emissions effectiveness. What this basically tells you is that intermittency of tanks is a big issue that we need to note down, because technology performance is critically dependent on that. Like, they're actually able to see the tank level emissions, but because the tank level emissions are intermittent, you have to make sure that you're comparing only those sites where the tank emissions was there during both measurements.
Hey, Arvind, could you repeat again the circumstances under which the methods improved their efficiency? What they were taking into account the intermittency? How?
So this is our analysis. So the technologies didn't improve anything. So what happened was technologies tell us, at 50 sites whether the tanks were emitting. We know from the baseline OGA measurements which of the sites had tanks emitting. And so these numbers here, the tank percentages were calculated by, okay, what fraction of the baseline emissions where tanks were emitting did the new technologies find? And these are the numbers there. But now what we do is we go back to the baseline emissions. We remove every tank that was noted as intermittent, and we then compare again to what the technologies found. And what we find is that when we remove the intermittent tanks, the effectiveness of tank detection increases. And so it's not that the technology itself improved. The technology detects what it detects, but because of the way field studies conducted, and because the technology team and the baseline team are not exactly at the same time, it might very well be true that the OGA camera sees a tank emission when it's there, but the next team that goes and does not see it because the emission has stopped. And to account for that, we just removed those intermittent emissions and calculated what effectiveness these teams have at tanks, and that effectiveness number increased.
All right, thank you. So did CCOPS kind of get lucky that every time they were looking at a tank, where those tanks leak intermittently, they happen to be leaking when CCOPS was looking?
Yeah, it's not that they got lucky. It's because of the way they work. So if you remember, CCOPS, they sort of survey about 5 sites a day. So on any given site, they might be there for like 45 to 90 minutes. So even if there's an intermittent emission, if they do like multiple passes near the tank, they will at least detect it one time. The the reason they're 100% is they linger longer at these sites, and therefore they're bound to detect an intermittent emission when it happens.
Got it. Thanks.
I mean, again, that's sort of the trade-off between, if you do a slow survey, you're more likely to find these intermittent emissions, versus if you do a fast survey, you can cover more sites at the same time. All right, I want to show this one because this is important. So what we did was, quantification is a really difficult challenge. Most technologies did not, they were off by anywhere between 50%, so 50% higher, to almost an order of magnitude higher. So what we did was, and I want to caution here because these are all producing oil and gas sites. We do not know what the ground truth is. This is not a controlled release measurement. So when I say that the technologies perform poorly in quantification, it's not necessarily because the technology was bad. It was because the emissions they measured were different because of intermittency, or because the weather conditions were very different when the technologies were measured. So what we did was we took the emission estimates that these technologies developed and the OGI baseline team developed, and we ranked the site from 1 to 50. So highest emitting site is rank 1, lowest emitting site is rank 50. We did that for the OGI camera, which is a baseline system on the x-axis here. And we did that for every single team that participated, their ranks based on their quantification. And we looked for the parity. So what this means is, so I'm going to talk about one technology team, Aerometrics, which I've pulled out here on the right. It's a drone-based technology. And so they have a reasonable correlation between the OGI rank and the Aerometrics rank. What this means is the highest emitting site that OGI found is also the highest emitting site Aerometrics found, even if their absolute quantification numbers are very different. What we did was the gray shaded bars will basically tell you 10%, 20%, and 30% error. But what is the top 5 emitting sites in your baseline? That's 1, 2, 3, 4, 5. This is also the top 5 emitting sites for Aerometrics. And so this is comparing the rank of emissions. And technologies seem to be reasonably effective in ranking the highest and the lowest emitting sites. I think this sort of more important and more of a reliable indicator of the detection effectiveness of these technologies than direct quantification measurements, because there's a lot of uncertainty that goes into absolute quantification. I think in future field trials, thinking about how we are going to monitor and to evaluate quantification is really important, because there's emissions are very complex and vary quite a lot over time as well. All right, and I want to
Arvind, on that
yes.
on that one example plot, may I ask a question?
Yeah, go ahead.
Can you talk about the highest ranked OGI ones, like, I don't know, it's about 27 or so, that are far outside the parity line? What you conclude from that?
I'm not completely sure. I mean, I have to look at the data and see exactly what those two sites were, but it could be possible that it was one of those scenarios where there was an intermittency, or the technology couldn't measure all sides of the site. Like, there were also access issues in some of them, like you cannot go downwind of these sites and things like that. It could be one of those, but I have to look into exactly why those two outliers are. All right, and the last thing I want to talk about is sort of what did I learn from all of these things? So one of the important things is that intermittency significantly affects detection and site level quantification. We had a couple of handheld teams similar to OGI cameras, but they are not OGI technologies. They did not show any significant advantage over OGI-based surveys. They were similar in many respects. Planes and trucks have distinct advantages in survey speed. But if you're going to effectively screen for high emitting sites, you kind of need reasonably good quantification to be able to say which one is high emitting and which one is low emitting. Drone systems are more effective at identifying emissions that might be challenging for other technologies due to access or location. And one of them is tanks, emissions from tanks, or even flare locations. And the last thing is in-field quantification is really a challenging issue. And that should be one of the strongest considerations while designing field studies and while evaluating the quantification properties of many new technologies. But with that, I'm going to stop and see if there are any more questions.